Jiping Jiang. He's coming from the Southern University of Science and Technology, and he's visiting us today, and we are honored to have him here to talk about his research about this first principle of the rational decision making and the design on water quality management. Thank you.
Thank you. Exeter University is really a very honorable place. I've known here for more than 20 years, and it's my first time here. I'm very happy. Also have a talk with someone online, someone here. I'm very happy to be here. This is really famous in China. I think a lot of maybe from Chinese in our area. For me personally, I currently is in PWR. It's in Newham, Utrecht. Visiting for 3 months. Then I come here for a short visit to Professor Fu and Professor Chen. I based on Shenzhen, Southern University of Science and Technology. It's only 10 years old. Previously, I graduated from HIT, Harvard Institute of Technology. And now the lecture here is the first principle of rational decision making and mainly focus on the water quality management. I will go details. Okay, then let's start the main topic of today's lecture. So for how environmental decision making is very general words, and in our scenario, some water-related scenario, we need to make the decision on what resource management or determining the use or allocation of water resource, or optimize the balance of water supply or demand. And the second analysis scenario is, for example, is water quality monitoring, set up the vast stations or the frequency of data collection. And the third, for example, also water ecology, ecosystem recovery or conservation were also some very detailed scenarios. Then we jump to the idea. So from the data, then we get the physical insight. Data is the physical insight of the real world. Then to make decisions. So the fundamental rule of the model is for example, the first principle, the mass balance, for the nature process. And for making decisions, so what's the fundamental rule of decision making? So we think about the term, it's first principles. So as comes here. So normally when making decision, we think about the maximum efficiency of system, or make the lowest energy, or the most robust status of the system in question. I think we can find a lot of examples to fit in those classifications. Then also, there will be multi-objective decision making or optimization, then relative to cost and benefit. So I do the literature search. I didn't find any paper talk about at least on water-related area or environmental management area, summarize some general rules. So this is just what I'm thinking is, for example, we can from the system point of view, then we'll be think about the energy of the system, the stability, complexity, performance. Then from another point of view, from the from decision point of view, the cost and the benefit or cost effective. So this I think is the fundamental thinking of this. Then, but for people, for decision maker is sometimes is not rational. It will be some analysis of it in behavior economics. For example, we will be for do gambling or do the lots, the very limited possibility you will got you win a bonus, but a lot of people still want to buy the lots because the value they think by the decision maker is more than the outcome, than the true outcome. So it's another story. So it's more from economic story for decision making. But for this, for today's talk or for our study, we only focus on the rational decision making. So this is the general idea. Then it's not, I mean, it's not a very new concept. It's from Aristotle, more than 2,000 years ago. Yeah. Then we want to jump to the idea of entropy. It's a big jump. So because this is a measurement of the complexity of the system, So it provides a good design standard for the optimization or decision making. Then, previously we mentioned what matters or materials or energy, but what is entropy? So then we go to the major issues. It's how to name it in normal words is kind of a degree of surprising. I think maybe many know this concept. So entropy and information entropy is a quantitative measurement of the system complexity. What I mentioned, you open a box, it's surprise, it's ordered or disordered. So we can use these normal words. Then it can be used for decision making, find the best decisions with the least energy cost or least complexity. So it's one of the first principle. Then it's basic idea, basic equations. So the normal one is this is the probability, and this log the probability of the random variable x. So x can be many. For example, the color of the box, a box of the ball, the different color. So x can be the probability of the box. And also, for example, in the river or in a tank, there are some ink in the water. So the probability can be the mass or can be the concentration probability of the grid or any kind of the particular mass from the tank. So there are other concepts, but this is a very basic idea. But I think this is not only just an equation, but also it's a kind of physical variables. It has some physical meanings because it are good measurement of the status of the system. Then we can use this idea to be used in the many decision-making problems relative to water quality. Okay, so in more than 60 years ago, so there is maximum entropy principle. It will be largely used in even in machine learning for training the models. But as early as in 1957, also is first proposed this. And there has been a lot of study in hydrology. So Jiping, the famous hydrology scientist, he published a paper in 2013. Then he made a focus on the stream flow, for example, and also designed the water quality monitoring network, and also how to select the model and the parameters. Okay, so from this tool or from this idea, so can we establish a decision-making criteria or a framework for what quality-related decision problem or design problem, and how to use in practice? Then previously designed is static, and can we to make the design to be action? Tell us what time should be take action to stop monitoring or start monitoring. So this is the basic questions. Then we set up some index, some fundamental index. Since we focus on the water quality, then first one is dilution index. So you still remember the previously equation. So the dilution index, so we think the P here is the how many mass in a box. So if we think about the river by a lot of grade of the water, so we pick up one box and how many mass in this box. So this mentioned it. So this is dilution index. It's not this index is proposed by about 10 years ago by Stanford by Kitandis, professor on underground water. Then also we propose a spatial entropy index. Then if we define the probability on the spatial, how the proton distribute along the x direction or y direction, and this is the temporal entropy index, and how the concentration change in a fixed time. So we set up 3, and also we think about the flux index in a fixed time and space, how many flux will be in the box in the time-space grid. Then this is the fundamental framework we set up. Then they can be used to different application scenarios. Then I will introduce later. Here is the equation, how we calculate. So we use a term prism, So the prism means we see the sunshine, and use prism, we see different colors. That is like different point of view. So from this entropy prism, then we can abstract the information from the process, or we can link the nature to the decision problems. Okay, this is the table, the diagram of the whole framework. Then there are some cases and also application cases. These are examples how we use this kind of the index in practice. Okay, then it comes another question first. After we jump to the application, if possible, we can develop some analytical solution for calculation. Because we do analytical solution, it will be very easy to do the theoretical analysis. It can be more easy for us to analyze some phenomenon. Then we just focus on one-dimensional stable transport. So it's very normal in some rivers. Then we try to derive this kind of analytic solution. So just report the main idea. So we define this is transport breaking through cube. Then we divide those cubes with the different, for example, divided by 10 box or 20 box. Then we calculate we got the variables to describe the distribution of the concentration. Then we have the analytical solution of the transportation. Then we use the identification definition of the entropy. Then we finally derive the equation of the analytical solutions. I'm not sure too much for the analytic solutions. Then with the solution, then we can use for many cases or for many applications. Okay, so this is the solution. Then we published last year. Here, this is the formula, and this is the G entropy, the special entropy, equal to this will be shown later. It's relative to Peterle number. So it's a number in hydrodynamics. So it's relative to the how strong the dilution or the diffusion. How strong the dilution compared to diffusion. So they have these styles. Then we collect the data from the about in 1990s. There are many dye experiments. Then we collect the field data. Then from the field data, we do the Q fitting. Then we find this equation is good. So it's but here is an outlier. But we also discuss why it's different. So now I just jump here because some numerical issues. Then we go to the application. So with the entropy, with the index framework, so how we use it? Then the first one is also is a very popular. Is the multi-network optimization. Currently, we also have many discussions with the industry. Even in China, I think they have a lot of money to investment in sensors or network or in the river. But we still need to make it more efficient with the fixed budget to make the network more effective. So here and in the big data side, in the big data age, so this kind of requirements began to be more and more popular. Then this paper, they use entropy-based method to optimize an existing ring-gauge network. So it's mainly focused on the hydrology or ring gauge, and it uses the joint entropy. So with a few sensors. Then what we use design is we use the transform entropy. So how to make the information transfer from the upper station to downstream station to be the maximum transfer. Then with this basic first principle ideas, we can design the monitoring network. So this monitoring network is used for tracking the proton from upstream to downstream. The monitoring sensor network can be different functions. So for this function, we only focus tracking. I will tell you how we set up some network can be used for detect out where the pollution will be occur or not. So there will be different functions, but all of these network functions, we can also use entropy to help to design different functions of network. Okay. Then here is also there's another. It's used for drainage system. Drainage system. So they set up the sensor. It means they want to most quickly or detect the pollution invention in the drainage system, in the water supply system. Then to make sure the network is stable. So for example, there is a sensor here. So if the sensor have the large water quality data, concentration maybe 10 times then the threshold, it means there will be pollution come in this network. Okay, I think Professor Fu also used a graphic to the identification of the pollution source. But here is another relative problem. Here is we set up those sensors locations to identify which part will be have the. We set up those sensors to make sure we most quickly find the pollution invention, pollution source, or we make the lowest percentage. How to name it? So there are two different point of view. One is we make sure there will be 1% from we can detect. Oh, sorry. We will be, for example, 90% we can detect from this part. Then there will be some loss. And another point of view, we will be 90% to or 10% to detect all of this. So there are two. Sorry, I'm a bit confusing. So there are 2 point of view. Anyway, we can use this volume of, in this paper, we use volume of information to aid the volume of this location to do the optimization. Okay, here is the what I previously report is the how to set up the network of the pollution tracking from upstream to downstream. So the basic idea is also easy. So the entropy transport from the upstream to downstream will be like this. So we only need to set up some stations here and here. Then there will be enough to identify how the information transport, because it's not necessary to set up too much, for example, for these stations or for these stations. Then this is the station locations, and also the frequency. Do we need every 1 hour or every half an hour or every half a day? So what kind of frequency we can use? But the basic idea is you have enough money, doesn't matter. So here is it's like a data fitting. So from the collected data, how those data can be reflected the truth of the pollution transport. Yeah. Okay. At least all right. Okay. Yes. Then we do the Fourier analysis. Then we also use the entropy from the 1 hour, one hour caption or to 2 hour data every 2 hour sensing. Then we set up the threshold. So this, for example, is from every 15 minutes to every 600 minutes. Then how the entropy goes down. And we can set up some threshold. But the threshold it should be 90% or 95% is also very subjective. Okay, this is algorithm. So we just keep it. And we do Songhua River and the Chucky River. Chucky River is in America and in this area. Okay. Then the model we can use MAC, we can use EFDC, okay, whatever you want to use. But the result output, we can use our analysis framework to make our decisions. So it's what I mentioned previously, from nature to bridge the nature to decision making. Then it's also relative to pollutions. Then is identify the pollution source. So in network or the urban drainage system, we have many scenarios. For example, groundwater infiltration, for rainfall infiltration, and also some mistake of the joint pipelines. We just mentioned 13 scenarios of this. But anyway, so we mention it. Where's the pollution come from in such a complex system? But if we want to do study, we just start with a simple case. And this scenario is still very important in China. The local EPA, they discuss many times, but to be very precisely find the pollution source still very expensive. and that's why we need some good method. For example, we can set up a grid every 500 meters set up sensors, but it's very expensive. It's not necessary. So we need some smart tools. Okay, so there will be some chemical method or environmental DNA, or there are many another method we can use. For example, for isotope can also be used, but from my study, we use ICT and plus the algorithm. So it's numerical source identification. So it means we collect the data downstream, then find the release, what time to release and when it release, or how many mass it released. So it's an inversion problem mathematically. Then the question is, previous study also in practice sometimes is not useful because they collect two days data. Then it has resulted in the pollution, and you cannot find it. You cannot find the who released it. So it's meaningless. But do modeling test is okay. But in practice, we should do action very quickly. For example, in 5 hours, we need to find the solution. We need to find the pollution source. But can we believe the inversion model or not? Or does the inversion model in 5 hours will be tell you to this direction or not the correct direction? So this is in practice, this is the question. Okay, so for this practice question, there are many inversion algorithms have been reported, more than 40 or 50 methods. Then we use very basic, we use Bayesian. Bayesian, I think many know Bayesian. So we combine Bayesian deduction with the mechanism model. Mechanism model is proton transport, and we do the Monte Carlo to find the source parameter. So we set up some priori. I'm not sure you know or not. I give some explanation. So we set up some priori distribution. For example, we know this there will be in upstream in 5 kilometers there will be potentially the pollution source. So we use the priori probability is -5 to -10 will be previous in the average distribution. And also we think maybe in the middle night they will release. So we set up the priority probability will be, for example, -2 hours or to -10 hours, for example. Then we collect data, then we do the revision to update the probability. Then we to make the pollution source more accuracy to the real case. Okay, so this is very, well accepted probability method to identify the pollution source. Then we go back to the question: how much data is enough to help us to make decision? Tell us, oh, it's good enough. Then we go to the field to find it. Okay, then we do some hypothetical modeling. Here there are 3 sections. For example, we started this section. This means monitoring section. We collect data every half an hour. Then this pollution source is about 12 kilometers upstream. Then we have established model. We think the one-dimensional model is enough in practice, and a stable, steady model. Then we do the calculation, do the Monte Carlo calculation. Then we find out the likelihood equations. Then we do the MCMC. Then we find the pollution source. The pollution source is mass, how many pollution released, and the location, where the source, and the time, what time the source released. So we only think about the instant source, not continue for one night. Then we do this running for 20 times, then we get the median or get the mean of these parameters. Okay, this is the basic idea. Then we find there will be some turning point. When the data accumulation, there will be some turning point occurs. Then we think this is kind of critical time. So when it comes to the critical time, then we can do the action. Okay, then so what kind of factor will impact the appeal of critical time? Then we do different cases. We set up different cases, set up different location of the monitoring. We set up the noise of the input date. We also test the hydrodynamic of the river, the different diffusion and the different speed of the river. Anyway, we set up about 20 cases. Anyway, then we go to the result. Then we find the occur of this turning point is relative to what we mentioned previously, the P number. So P number also relative to the entropy. So is the complexity of the identification system. So here L and D, here the L is a bit tricky because we give a direct L is sometimes subjective. It's the length of the question. Anyway, with a lot of calculation or tests, then we find a very interesting equation that this critical profile. So this point is how many dates we needed. So we propose a relative critical time. So it will be have a good relationship with the PE. There will be, but this dot is not good. So we try to explain. It's still not finished. We try to explain why this point is not good. But at least we can use this curve to help us to identify what time we can take action to go to the field. So when we collect enough data, when we arrive at the relative critical time, then the result is acceptable. Okay. Okay, this is some analysis of the relative critical time. This is our observation interval every 2 minutes, or every 4 minutes, or every 15 minutes, and also the error what I mentioned, or 1 station, 2 station is different. So what we test, this curve is only relative to one station monitoring. But if we do 3 stations, so the relative time will be much smaller. Okay. And with this, then we find the basic rules, how to set up the source identification rules. Previously, we need to understand, we need to get the basic parameter of the river, the diffusion coefficient, the cross-section area, for example. Then based on these basic parameters, then we can set up this network and the monitoring plan before we very quickly before the event has have occurred. Okay, it's almost for talk about the entropy. We mentioned from how the static design, from the checking, pollution checking, also pollution source identification. We can also use this from the point of view of the complexity of the system to help to design the network. So from the first principle thinking. I'm just starting and want to make more things together. I mean, make a bigger framework. What's interesting is in last November, there are #1 scientist in China, Qu. He is the director of Natural Science Foundation of Environmental Science in China. He also did a report in a very similar topic, first principle in environmental engineering. Okay, anyway, I don't know, and also Elon Musk also used this kind of talk in a lot of his talkings. So I think it's a good methodology for us to think about the academic questions. And here is another decision making. I want also make this to be under the framework of the first principle is how much cost. I mean, we directly to the cost. The question is, should we use distributed model or undistributed model? I mean, centralized mode, collect the data with the pipeline, or just collect the data without pipeline, which they established with WWTP. So in rural areas. Then this question is very important for decision making in provincial government or in national, in central government. In what will happen in East China, in South China, or in North China? What kind of mode, distributed or undistributed, is most suitable or not? So also this kind of decision making problem, we just go to the basic rules. I mean, we just calculate how much we need to pay for this. If we set up these different models, then we set up the basic ideas of the is kind of economic, financial accounting, or how much we need to pay for this construction and also operation. Then we got some result. Then we got some curve of the what will be relative to different population, different income, and different landscape. So these three factors will impact our decision, impact the financial. So it's also, I think, it's kind of first principle. Previously, the calculation of the construction cost is very complex. A lot of book or design, but we just forgot it. We make it simple. We just get a very generic calculation of the cost. Then we got some very interesting ideas. Then we got these pictures. I think it's very beautiful. They show us in which part is most suitable for which kind of the mode. Then we got the map of in the rural area, in the rural level, in which kind of the treatment pattern is most suitable. Then it's for Guangdong province and for Hunan province. This is the result. Different color means different mode is most suitable. For example, this is with pipeline, and the yellow is distributed model. And we also go to the village to check and contact the central government to collect the data or collect the field data. The result is stable or not. Okay, anyway, so this is all my speech, and I'm more open for discussion. Then, from the previously framework, the entropy, I think it will be useful, but when I discussion also with some professors, I think we can also think about from another point of view, from statistics point of view, to provide another way. But anyway, I think it will helpful in practice. Anyway, there are some of my team help to this, and final dessert. One page dessert. So this journal hydrology is more focused on hydrology. I think that some of study here is also relative to hydrology is from the journal T, previous the T of journal hydrology X is exactly same as what the journal of hydrology. Okay, yeah, yes. And now in this year, they want to make it to be letter, only 400 words, and very quick letters. Then we are inviting top scientists to contribute to this. So I think it's someone very exciting result, but you want to publish quickly and just 2 pages or 4 pages, please think about this journal. Okay, thanks for Professor Fu and Professor Chen. Yeah, welcome your comments. Thank you.
Thank you. Thank you, Dr. Jiang. Any questions or comments? Yes.
Thank you very much for your presentation. My first question is, I'm interested in your topic about the entropy-based method, to use this method to optimize the ring gauge. And could you please, speak more about this content, like how to optimize the ring gauge and what kind of the factor do you optimize, like the location of the ring gauge or the quantity of the ring gauge? This is the first question. The second one is about the Bayesian method. You use that to track the pollution source. And I know the Bayesian method, we need to, there are a lot of mathematical theory behind this method, and how, you need to define the likelihood function, the prior distribution function, and how do you get this function, how do you get this likelihood of these pollutants? Yeah, thank you very much.
Okay, the question to a key point. Yes. The first one, the ring gauge, the study is finished by a team in Nanjing University. I think it's not by mine, but I can explain a bit. Okay. So the basic idea, I think, is similar. So what they do is, now they have 100 gauge, yeah? Then they just decrease the gauge from 100 to, for example, 50, to 50, yeah, to 50. Then they need the ring gauge data for each station. They have the probability, they have a historical data. What they do, I think they just calculate the, for example, they select 50 let's from 20, okay? From 80 gauge, then they calculate the entropy between 80 and 100. Then also they calculate the 60, 50, and to minus. Then for every 50, they have a different combination. 50, yeah, select 50 from 100, then they calculate the entropy and compare them. Okay, I think this is basic ideas.
Okay, thank you.
Okay. Then the second one is, it's also some assumptions. Assumption that you mentioned the likelihood. So the likelihood here, so we assume the noise is normal distributed. The normal distributed. So from the output, there are some errors. So the errors means the observation minus the prediction output of the model, right? There will be a error, right? So from observation minus the output of the model, then we assume this normal distribution. Then we use we get the likelihood, the likelihood of this function, this assumption. Okay. Then we use the Monte Carlo to do a lot of sampling. We cannot get the formula in this case of likelihood function, but we can do the adaptive liaison algorithm to Monte Carlo to get the degree, the probability distribution of the likelihood function. Okay, we cannot write down in analytically what is it.
Okay.
All right. right?
You use another Monte Carlo method to produce the...
Yes, to produce the distribution of likelihood. Yes. In some case, it will be analytical, it can be analytical expressions. Yes.
Thank you.
Thanks.
We still can have one quick question.
Thank you very much for the nice presentation. It's very interesting to see the ideas about the map, from the data and the model and the system integration. Right? So I think the chain of from data to system integration. So I wonder the entropy-based approaches, are they more suitable to deal with the data-related the problems, or are they suitable for the system integration in a more higher level? I understand that from the data to system integration is going higher level, is more complex. Right? So do you think the entropy-based approach are suitable for system integration, dealing with system interactions, this kind of issue?
Yeah, maybe it also works, but at this stage, yeah, I focus on data-related. Entropy should be, it's kind of viewpoint of the system. If the system can be described by data, then we can use this measure of the complexity of the system. Yeah, so I think from the data, at least any relative to data, then we can use this index to measure.
I'm giving a lecture.
Yes, I'm finished.
Okay, sorry.
Sorry.
And what's your second system integration? You mean?
Yeah. I think that's fine. So I think probably you answered the question.
Okay.
Thank you.
Thank you very much, Dr. Jiang. And because you see people are coming for the next lecture,
Okay.
so could you please join me to thank Dr. Jiang for his presentation? He will be with us today, later this afternoon, so you should be able to discuss with him further about the details.